The reason that Laura invited me is that we just had our third workshop 2 or 3 weeks ago, and we went from those 8 sites. We spent 2.5 days talking about each one of those sites in as much detail as we possibly could. And we voted. We had 200 and some odd people at our workshop, and everybody got to vote. And this list is almost like what they voted with the slight minor changes. And the 3 sites outside of, again, the white ones were already there. The 3 sites that were selected are Jezero Crater, Northeast Syrtis, and the Columbia Hills. And you'll notice that the Columbia Hills is right next to where Spirit landed. And that's because Spirit found something that could potentially be of great interest for the next one. So, just rocks. What's making these places so cool? All right, here we go. First out, Jezero Crater. This is a large impact crater. Goes all the way around like this. You can see there's a map channel that comes in here. That's shown here from an enormous catchment basement through the ancient highlands on Mars. This site dates to about 4 billion years in age through nefarious means. This crater filled up with water, and this stream carried water into this lake, and it created one of the most distinguishing geologic features that we know of. And this is a delta. This is a fan where water carrying sediments from that huge catchment at 4 billion years ago on Mars hit an open body of water, and that delta sorts the material that is brought into it by the river. So think about the Mississippi River at New Orleans, where it's carrying all the sediment from the United States out into the Gulf of Mexico, and it sorts it by size. So the bigger stuff is going to fall. It hits a standing body of water. Big stuff falls out first. And it progrades and grows out into this lake in a system of what are called top set, 4 set, bottom set beds. And the bottom set beds are out in this nice, quiet water. The little boogers can do the backstroke. There's almost no sediment except clay-sized particles. And clay-sized particles to a geologist are micron size. They're really small, and they've been already water processed to get them to be in that size. And they slowly filter out of the water. Calm water, warm water. It's liquid, right? It's not too cold, not too hot. Liquid water, the clay, and all the little guys that are doing the backstroke. And after they die, they fall on the ground, and the clays entomb them. And the clay is a wonderful sequesterer of any kind of bioorganics that exist. And these are among the most fertile places on Earth. And we can see that same arrangement of top set, 4 set, bottom set beds in this delta. So we know that it formed into a standing body of water. It carried sediment from a huge chunk of the highlands that already had clay minerals in them, these iron, magnesium smectites. And it was from a large catchment area, and it came out into this body of water. And if there was things floating around there, it's preserved in the bottom set beds of the delta. Pretty cool, huh? All from a little bit of geology. But let's say you went there and you couldn't be sure that there were actually little bugs in the clay. In addition to that, there's carbonates in outcrops that come out from, this is our ellipse, by the way. It's about 10 by 8 kilometers. That's as good an ellipse as we've ever been able to do. It's nice
and by ellipse, you mean landing ellipse.
Landing ellipse, yes.
So can you say just a word what that is so people know?
So basically the spacecraft, this is going to get complicated, but stay with me. So it's going to come in, and it actually has to be targeted to the outer part of the atmosphere at about 10 degrees off of total skip out. So if it comes in any shallower than that, the spacecraft will, like you're skipping a rock. It will actually skip off the atmosphere and keep going. That's not a good thing. if it comes in any steeper, the flight path it takes is not long enough for the aeroshell to slow it down enough such that the parachute would be able to handle the speed it was going to when it came out. It has to hit that. It has to hit it to within, a tenth of a degree. Okay, so here to Mars, remember it takes 9 months to get there, moving at several kilometers per second. So it's not dawdling, and it's got to hit this spot at just the right spot and angle, such that the flight path it takes as it comes through the atmosphere will carry it to that spot. And we don't know where in that spot it's going to come down, but it has a 99% chance of. And there's always one that's going to be outside. Okay, so within the ellipse is the area that you're most likely to get to with your rover, because everything's close. And the closer it is, the faster you get there, and the more you can do science with it. So in these areas beneath this cover are carbonates. What's so big about carbonates? On Earth, all carbon cycle is modulated by life. Now, the Earth is lousy with life. Life's everywhere, and it modulates just about any organic functions that exist, and carbon's the number one element for that. So if you strike out there, you got carbonates, and if carbonates were biologically mediated on Mars, there's the great place to go. And the last attractive thing about this site is it has this cover, this gray unit that you can see. And the way we date things on Mars is by counting craters. But we don't know exactly how many craters go to a particular radiometric age. So if we could bring back a sample from a surface that was big enough that we could count the craters on, bring it back and get the age of the sample, we could calibrate that crater curve. Well, wow, that's great. Now we've calibrated our curve, and when we count craters, we actually know the age better than a factor of 2 or 10 or whatever. Okay, so those are the things inside Jezero crater. And this was the highest ranked or most favorably voted of the sites. And the reasons are just as I said. Okay, number 2 site is Northeast Syrtis. And interestingly enough, here's the ellipse here. It's 8 by 12. And even more interesting, I just think this is totally cool, this is Jezero crater here. So if you got tired of this site, you just go over to Jezero crater. It might take a little while. It's several hundred kilometers. Okay, this site has basement rocks that are 4 billion years old because it's sitting right next to a giant impact basin that has to be at least that age, called Isidis. And you can see these mesas with high-standing scarps of what are almost certainly different layers of rocks. And you can see those rocks are exposed and fractured and broken up. So there's rocks sitting at the surface available for our rover to investigate it. And we've got 2 or 3 different rock types in a stratigraphic succession. So I can go there and I can say, what's this? And how do things change when I went a little bit younger? And how did it change when I get a little bit younger? And so on. And the materials that these layers are made up of are clay minerals. Clay minerals form if you take a primary igneous mineral and you chemically erode it with water. On Earth, that happens all the time. That's clay, is dirt, is so on. You break it down, you change the mineral structure, and you add water. And in order to make a clay mineral, you gotta add water. Well, if you've made minerals that had water in them, that could be an aqueous environment, one in which liquid water was there. So here we've got 4 different distinct environments with very different clay minerals, both iron and magnesium as well as aluminum fiber are clay minerals. And they all have different weathering paths that take slightly different environments. So we have different environments in some of the oldest rocks on Mars. At 4 billion years, Mars had a magnetic field. That magnetic field would have kept all harmful radiation away from it. We think that could have been the most habitable time on Mars. And here's rocks and layers that are chemically processed. In addition, just a little bit further away are these big flat tongues. These are middle-age Hesperian on Mars basalts, which are primary igneous rocks from the mantle. And these are the key. If we could get a piece of that rock back, we could totally calibrate our crater curve. So that's really liked. And then just underneath it is sulfates that are deposited just prior to that. And those sulfates from our work on Mars is suggesting a very acid environment. So it looks like you went from a neutral pH environment with these clays to an acid environment in the sulfates to our friendly basalts on top. So pretty cool spot. Okay, last one. Oh my goodness, this one has a rock hammer. So this is not from orbit. That's your first key, because we know the size of rock hammer. This is the Columbia Hills. This is where Spirit went as the last part of her mission. And it came across these nodular structures of light-toned materials that were quite hard. We discovered them because one of Spirit's wheels was no longer turning, and we had to drag it across, and it actually broke apart this material. And we looked at it close up, and this material is 91% silica. So the only way we know how to produce that material on Earth is in hot springs. Okay, so don't think of geysers, but think of little hot springs coming out of the ground and going down. And on Earth, hot springs are teeming with life. And they're teeming with a kind of life, we call them chemists. They're autolithotrophs. They live off the chemistry of the water, the minerals in the water. They're not living off the sun. And those are among the oldest and most ancient life forms on Earth by looking at RNA tracking. So if this was on Earth, and here's an analog at the same scale in Chile, up in the Atacama Desert, where you have these same little nodular, again, 91% silica, teeming with life. And the silica comes out, and it sequesters, it entombs the things that are living in the hot water. And so this is a great place to sequester any of those tests from the animals that lived there at that time. In addition, there's a diversity of materials within the Columbia Hills, including volcanic rocks, including that middle-aged basalt. And so this would be a location you could go back. And so the three spots that we've selected are three places where on Earth biologic activity thrives. Deltas in the bottom of a lake, in a hot spring, and I failed to tell you the environment for this one, which is, we think we're probably in groundwater here, just slightly beneath the ground. Some of the minerals here formed under a little bit of pressure, so we think we were just down under the ground. And on Earth, 90% of the biologic activity is actually living down under the ground, and it's these same sort of chemolithotrophic organisms that live off the chemistry. So the three places on Earth where we know that primitive organisms thrive and live, and where you could both have those organisms live and you could potentially sequester the materials that form from them, are the three sites that we have down selected to for 2020. And given the main objectives of the mission of trying to find a place where that material is, and it could have sequestered that material, those are three great places. So where's 2020 going to go? And you'll have to invite me back in about a year and a half, because we will have. So in a year and a half, we will have probably our last workshop. We hope to have all the scientists come back and have arguments for why each one of these sites is the best one that we should go to. And those would be narrowed down and brought to the Associate Administrator for Space Science at NASA for a final selection.